Hi, Chris Kuzmal here. Today we are going to be beginning our BC calculus work by considering the area and length, and I put that in quotation marks, of an annulus, also known as a ring, and that's this red area in my GeoGebra window. I have set things up so I can change the width of the ring, and that's done by creating two circles. One circle has a radius of 5, and the other circle has a radius that's 5 plus this thing I call dr. So the area of a circle is pi r squared. So the area of our example inner circle is pi times 5 squared, and the area of the circle, which is the combination with the overall circle, the overall larger circle, the area of that is going to be pi times 5 plus dr squared. Okay, so that's the answer. Oh, and then so then the difference between the area of the larger circle and the area of the smaller circle is the area of the ring. And then the cool thing is the ring's area. Well, let's think about if as the limit as dr approaches 0, it kind of becomes a line. So what's the width? The width of our line going around our circle. So the width of our radius is approximately dr, and so the area is going to be, if we know the area, if we can compute the area and divide by dr, that'll actually give us the length in the limit as dr approaches 0. So that's the answer. Let's put it all together. Let's look at code solving this problem step by step. Okay, now I'm not going to type out the code as we go. I'm going to read it off. So I apologize for those of you who prefer that I type it out, but uh, there's just too many letters here to type, and I'm afraid I'll make too many mistakes. First thing we do is we create a variable of type double that has an inner radius of 5, and another variable of type double dr whose value is 2. Notice that in our GeoGebra situation, dr can vary. In our code here, we set it equal to just 2, and we don't have it. I mean, it's a variable, we could change it, but there's no sliders obviously available. Formula. The inner circle's area is just pi times the inner radius squared. Okay. The outer circle's area is pi times the inner radius plus dr, and we square that by multiplying it by itself again. So the ring area is the difference between those two. Another way of expressing the ring area is taking the difference between, substituting in the outer circle area formula from line 9 and the inner circle area formula from line 8. Substituting those in, we just get pi times the outer radiuses squared, which is going to be inner radius plus dr times inner radius plus dr, minus, don't forget this minus sign, the pi times the inner radius squared. All right. Yet another way of doing this is to pull that math.pi out. We factor it out. So math.pi is sitting out here, and you'll notice we add parentheses. So all we did was we factored out the math.pi, which is just pi. That's just pi. Okay, math.pi is just the variable, the value of pi. But yet another way of doing this is we can multiply out the inner radius times dr plus inner radius times dr. That becomes inner radius squared plus 2 times inner radius times dr plus dr squared. All right. Well, the cool thing is that means the inner radius squared appears twice, one time as a positive, the other time being subtracted off. So we throw those away, and we have pi times 2 times inner radius times dr plus dr squared. Okay, well, this is the area, remember? So if we divide by dr in the limit as dr approaches 0, that's going to be the circumference. So we divide by dr, and which is just next RA divided by dr, which is just math.pi times 2 times inner radius, because remember, inner radius times dr divided by dr, we have an inner radius, dr times dr. So this is the circumference. In the limit as dr approaches 0, dr, well, becomes 0, and the circumference is pi times 2 times r, 2 pi r. That is, in fact, what we know from geometry to be the radius. So we used calculus-ish type things to figure out what the circumference of a circle is based on the formula for its area by doing, effectively, differentiation. Welcome to calculus.